Hello everyone. We're starting a new module called Support Vector Machines. And specifically in this section, we want to discuss linear support vector machine classification. So for this module, we have three major components: linear SVM classification, nonlinear SVM classification, and SVM regression. So you just be aware that support vector machines can not only be used for classification problems, but also potentially be used for regression problems. What is a support vector machine, or specifically, what is a support vector machine classifiers? We call it SVC. A support vector machine, SVM, is a powerful and versatile machine learning model. It's capable of performing linear and nonlinear classification, regression, and even outlier detection. SVM classifier as fitting the widest possible street. So pay attention to this word, widest possible street, which is represented by the parallel dashed lines between the classes. This is called large margin classification. Suppose that we have this data of that iris data, and you want to use petal length and petal width to be two dimensions to figure out the classification boundaries. Then you could have all kinds of separation, right? This would be one way to separate those two classes. There will be another way to separate those classes. And one more way would be looking at this one, which is in the middle of two classes. And the good news is, in this case, it actually have largest possible, widest possible street, right? So if that happens, then this would be a support vector machine. And then we have special names for these points that actually lines on the boundary. It's called support vectors. This graph is trying to illustrate it really helps if you scale your data for SVC. So for x0 versus x1, x0 is running from 0 to 6, x1 is running from 0 to 70, 80, right? And then if you don't scale, you end up with this support vector machines, and then the street is not as wide. But on the right-hand side, if you scale the data for x0, -2 to +2, and then for x prime from -2 to +2 as well, x1 prime from -2 to 2 as well. So that way you find that your SVC is doing a much better or easier job for the classification. So it would be better to scale your data in SVM scenario, in SVM context. So what we just discussed is something called more like a hard margin. You don't want to allow any violation. But the reality is, for hard margin problems, you are very difficult to the algorithm tend to be very difficult to come back with a good solution if there are outliers. In this example, for example, if you have an outlier, one of the different classes of flower, then it's impossible for you to come back with SVC to to differentiate those two different classes just because of this one outlier. And also, if you have another outlier in here, then just because of this one outlier, instead of have very wide street, now it becomes very narrow. As a result, SVC theory actually comes back with something called soft margin classification. Essentially, what it does is it is trying to find a good balance between keeping the street as large as possible and limiting the margin violations. In this case, if it's soft margin classification, you still can come back with a good support vector classifier with this one violation. Same thing for here, you still can come back with much wider street. So this concept is called soft margin classification. In soft margin classification, there's a hyperparameter that you can adjust. This hyperparameter is called C. When C is small, what happens is you actually allow for a larger, wider street, but meanwhile, it actually allows for a lot of violation as well. But on the right-hand side, you can see the C is much bigger. It actually allows fewer margin violations. As a result, the street is narrower as well. So in support vector machines, you could use this decision function, that is a specific line, wx, wt times x plus b less than 0 to be 0 and larger than or equal to 0 to be 1. That would be our solid line to differentiate those two different classes. That's called decision function. And then in this case, you could, same thing for the iris flower data set. When h equals 0 would be the solid line. And then if you allow for positive and negative to differentiate those two, then you have a positive 1 and negative 1, which would be the dashed line to differentiate those two different types of flowers. Here, trying to give you more explanation on what exactly happening in support vector classifiers. So in this case, if we define something called T, for before we do that, actually one thing you should be aware on the top right chart, what's happening is W. So we have that Wx plus B, right? When W is small, essentially says that the slope of the line will be small. Smaller comparing to larger slope, right? When the W is smaller, what you saw here is that the margin, the distance between those two dashed lines, that's called margin. The margin is actually bigger. Essentially, this point, the distance from here to here would be around 4 units versus here is only 2 units. So when W is smaller, the margin is bigger, meaning the street is wider. So we're almost trying to minimize this W, trying to minimize a W so that the margin of that classifier is as wider as possible. The reality is actually we're trying to minimize a half of W transpose times W with certain constraints. If you recall that we have WTx plus B larger than 0 or less than or equal to 0. If we define a new variable that is called t, ti equal to -1 for negative instances and ti equal to 1 for positive instances, so that we can put them together as one constraint, ti times this wx plus b larger than or equal to 0 to be one constraint. It's sufficient to be the constraints for hard margin linear SVM classifier. So now if you look at this function, its objective function is 1/2 wt times w subject to this constraint. This particular function form belongs to a specific family of optimization problems. It is called quadratic programming, which we are going to discuss shortly, very briefly. There's one more thing that you should be aware, right? We just discussed that hard margin. And then for soft margin, what it is essentially adding a penalty function that allows for a violation. So we introduce a slack variable that is c larger than or equal to 0 for each instance. C measures how much the ith instance is allowed to violate the margin. So once we have this c, we see that, okay, you don't really not necessarily need to larger than 1. Larger than or equal to 1, you could be larger than or equal to 0.9. And then you use that c to penalize your objective function. So this is called soft margin linear SVM problem. And as I just mentioned, for hard margin and soft margin, both of them belong to this special family of optimization problem. It is quadratic programming problem. And for quadratic programming problem, as you can imagine, the objective program would be quadratic. And then for this type of problem, the only thing that you need to know is you can leverage the do problem, because the do problem is much easier to solve. And then if you don't know what is a do problem, all they just need to know is in optimization, there is a primal problem, there's a do problem, they're actually equivalent, and sometimes it's easier to solve the primal problem, sometimes it's easier to solve the do problem. So in this quadratic programming problem that we are dealing with in support vector machine context, the do problem is much easier to solve. And here, just to give you an introduction on how you can actually implement the SVC in scikit-learn. You could have 3 different possibilities. One is called linearSVC class with c equal to 1 and the hinge loss function. Of course, here, this pipeline, you actually do the scalar first, because we said scaling helps SVM algorithms. You scale them first, and you do linearSVC with c equal to 1 and loss function being hinge. This is equivalent to leveraging SVC directly rather than linearSVC. You do SVC, kernel function being linear, and c equal to 1. You could also leverage SGD classifier, loss function being hinge, with this alpha equal to 1 over m times c. Once you build this SVM classifier, CLF, you can predict what would be your classification of corresponding petal length and petal width as a specific input, which class it belongs to. Okay, This actually concludes our discussion on linear SVC. Thank you.